Thank you. So that's a good reminder. Well, thank you for checking. The rest of the class should thank you too. Collectively, give you a Starbucks, gift card or something. Okay, because this class is kind of important because it's the practice final. Okay, so in this case, I'm not commenting the program. You kind of have to figure out what the C code is doing. So since we're only talking about the practice exam, I can explain it. But in the test, you will have to figure out what the code is actually doing, or you can just do a blind translation if you don't need to. You don't really need to know what it does. Okay, you just have to make sure that your assembly code gets the same job done. But understanding what it does is important. It's kind of helpful.
Why would you make this?
Huh?
Those are such weird requirements for parameters.
Parameters?
You have an unsigned int and then the at.
Well, unsigned n, because n is the size of the array, that cannot go negative. So that's why it's unsigned. And then the array itself is an array of signed integers. But the array can be an array of whatever, right? Okay. So we want to find the minimum of that particular array. There's a local variable which is result, but result is not a signed integer. It is a pointer to a signed integer. So if you look at what this program does, we automatically increment a and automatically decrement n, and we also initialize result to a, which is the beginning of the array. So the intention of the first 3 lines of the program is to say, let's assume the first element of the entire array is the minimum, okay? Because I haven't seen the rest of the array yet, but I can make that assumption. So the idea is I'm going to skip over the first element of the entire array, so I don't need to compare that to itself. Because otherwise I'll be comparing the first element of the array to what I thought was the smallest, which is also itself. That, at that iteration doesn't do anything productive. And I'm also going to decrement n, which is the number of elements in the entire array. Because the first element is already assumed the minimum, I don't need to compare against that. So the loop itself is fairly easy as long as there are more elements to compare, which is stored in n. N is a countdown, counter in this case. I compare whatever result is pointing to, which is supposed to be the smallest of the entire array, and I compare that to whatever a is pointing to. If what result is pointing to is greater than what a is pointing to, then I've just found a new minimum. So I update result, which is a pointer to the smallest element in the array, to what a is at that point. But regardless of whether the conditional statement fires or not, I increment a to move on to the next element, decrement n to remember that we have one fewer element to compare, and then go back to the beginning. So when this is all done, I'm just returning result, which is the pointer to the smallest element in the array. So I'm not returning the value of the smallest element, I'm returning the address of the element in the array that has the smallest value. Is that okay? All right. So to translate this into assembly code, okay, so I'm going to do it, using my stylus, just so that, it's kind of the same experience as, writing on a piece of paper. So in this case, okay, it's a little bit awkward because my hand is not long enough. So I have to move everything this way a little bit, make sure all the cables are still connected. Okay, cat hair. I have a lot of cat hair on my stuff. Okay, so in this case, the subroutine will start with a label, find min, and I think I can use a smaller, the pencil doesn't need to be as this thick. Let's pick a thinner text here. Okay, so find min, and then it has 2 parameters. So I'm going to use label definitions. It also has a local variable, which is result. So I'm going to say result is 0 because when after I do the allocation, the stack pointer should be pointing to result. And then after that we have return address, RETADDR, which is going to be result 1 plus. And then we have the first parameter, which is n. So that's going to be return address 1 plus, and then we have a, which is the second argument, which is going to be n 1 plus. So all of this stuff here is just defining the labels. So this way I can refer to the names of the label when I need to refer to items on the stack. And I don't need to track all of that stuff in my head. I can just refer to the symbolic name that just so happens to be the thing that I need to access on stack. Okay. So after this, I need to do a decrement D to allocate for result. Okay, so we have decrement D. And then we can do the initialization. So the initialization is taking the value of A, which is my argument, and then copying that to result. So depending on whether you want it to be like purely mechanical or whether you want to kind of do it as with the fewest number of instructions, that part is up to you. So if you want it to be mechanical, just do LDI with the name of the thing you want to access, which is A in this case. And this looks kind of confusing because it's load LDI AA. The first A refers to the register, and then the second A refers to the label. Okay, the assembler has no problem differentiating between the two because it knows the first thing in an LDI has to be a register, and the second thing has to be an expression. And you cannot use a register in an expression. So to the assembler, there's no confusion, but to us, it looks a little bit confusing. Okay, so that is the displacement from where the stack pointer points to the thing, which is A in this case, on the stack. So by itself, it is not that useful. You have to add the stack pointer to A in this case. So the A becomes the address of parameter A. And then, but because that's just the address, which is also not what I want, I need to have a LDA in parentheses A to actually get to the value of parameter A. Now, we have to be very careful here because you have to really make sure that you understand that we are accessing parameter A and not what A points to at this point. So right now, register A has parameter A, but not what A points to. A just so happens to be a pointer, but I'm not dereferencing A as a parameter yet. And then it's time to copy that to local variable result. So the easiest way to do it is just to do a store now, okay? Because the stack pointer is still pointing to the local variable result, so I don't really need to add 0 to the stack pointer or add the stack pointer to a register containing 0. So it's kind of a shortcut, okay? But it does help to reduce the number of instructions quite a bit. Yep.
When we decremented these in order to allocate the string to result,
Mm-hmm.
isn't it gonna change the offset when we do add A, comma D?
They are already it's already accounted for. So when you look at how result is defined, it is defined to be 0. So that means that I'm already assuming the stack pointer is in fact pointing to the local variable result.
Okay.
So the definition of the labels has nothing, absolutely nothing to do with the instructions. So I can have the labels defined entirely correctly, and then forgetting to adjust the stack pointer, then everything is actually wrong. Do you see what I mean?
Yeah.
So the label definition is really just a shorthand so that I don't have to remember the offset. But at runtime, whether the stack pointer is correctly pointing to the right thing depends on the actual mnemonics, the code that runs at runtime. The symbolic definitions are really just for assemble time, is for the convenience of me, but the mnemonics is what actually counts during runtime. All right, so now we continue with this. The second line is incrementing A, okay? So if you want to do it mechanically, you can kind of do it kind of in a long and very mechanical way. And I'm just going to be a little bit, well, maybe it's okay. I'll do it mechanically too. But this time I'll LDI C with A, and then we have a add CD. So D is now the address of A. I'll keep it in C. I'll do LDAC. So now we have the value of array A in register A. we do an increment, because what A points to only takes up 1 byte. So increment is going to move on to the next element in this case. And then we do stca to store it back into local variable A or parameter A. Is that okay so far? All right. So now we have the third line of initialization, decrement n. It's going to be about the same thing. So if you want to kind of use this, to say, okay, continuation up here, that's fine. So we'll do a LDIC this time with n, add CD, LD, A in parentheses C, but this time we have a decrement, and then we store it back. So it is important to remember to store the changed value back, because otherwise you're incrementing the value, but it is in a register. It doesn't affect the thing that is actually on the stack. So the store instructions are important in both. So it's kind of handy to store the value in one register so you can increment or decrement it, and then store the address in the other one. So this way you don't have to recalculate the address to store it. So it's kind of like a shorthand thing. So are we okay so far with everything before the loop? Okay, so let's go ahead and figure out what the loop is going to do. So this might I'm just trying to figure out, yeah, we can do it this way. Okay, so after this, this can continue at this portion, or if you prefer, you can go all the way back here. So now we have to deal with a while loop. The way I would do it is to write down all the necessary labels. So we have while begin at the beginning, and then we have a unconditional branch JMPI back to while begin, and then we have a label while end that is after the unconditional branch. So this much we can write almost in right away, because it doesn't even depend on the condition. Okay, this is how a while loop or pre-checking loop is going to look like in terms of labels, unconditional branch, and stuff like that. So now we have to go in and fill in, okay, so how do we evaluate the condition? I don't think the condition is going to be too complicated, so I will try to fit it within this blank space here, because it really just involves loading n into a register and then test it whether it's 0 or not. So now we have a usual LDI. We can use whatever register we want. We'll use A in this case, and it is n that we want to retrieve. Add AD, and then we do a LD AA. Oh, okay, I ran out of space. Okay, so in your case, you can do it the same thing, because the whole idea of me writing it instead of typing it, which I can do a lot faster, is to illustrate, if you run out of space, you need to say, okay, it continues here. You can do it like this, okay? So this way I can visually follow the arrow and go like, okay, that line follows this line. So this way you don't have to pre-plan, enough space and then figure out that, oh, okay, I didn't have enough space, or, do stuff like that. So you can do it this way. And then we can use the shorthand thing that we already know in one of the classes. So we can do an AND, A with A, because what this is going to do is it will actually go through the ALU, calculate the result of A bitwise AND with A, and then store that back into register A, which doesn't change anything in A, but it does affect the flags. So that's what we are looking for here. And then we'll say JZI, okay, if A is 0 at this point, which is actually N, then we'll go to while end. So that becomes the condition of this loop. Now we need to fill in the body of the loop. So to fill in the body of the loop, we'll just kind of go like, this code goes in here. Okay, or you can be very specific and say it goes in here. Okay, there we go. So this way I know, this chunk of code, whatever long, however long that is really a part that goes right here. Okay. All right, so we have to check what A is pointing to against what result is pointing to, and then we want to update one of those two if one is pointing to something that's greater than the other one. So I'm dealing with a lot of reflection, and that's why it's hard for me to actually see what I'm writing, because all I'm seeing on my screen is that these two banks of fluorescent tubes. I think if I turn off, it's going to affect the entire classroom and not just that bank. Yeah, so all the banks are connected. Is that okay for you guys to take notes? Okay. So with a conditional statement, it is you also have to evaluate the condition, but you don't need a label ahead of the evaluation of the condition. So we'll figure out what result is pointing to, and then what A is pointing to. So we'll figure that out here. So once again, we can do LDIC with result add CD, and then we have LDCC. That will get us result itself, which is a pointer to something. And then another LDC with C will get us what result is pointing to, which is what we need for the comparison. And then we'll do the same thing with A. So we'll do LDI AA, add AD, LDAA, LDAA. I know you guys cannot see that. Let me go up a little bit like that. Okay. So now we have register C storing whatever result is pointing to, register A storing whatever A is pointing to. Now we can do the compare. Oops. So when we compare, we kind of have to think about the order of the comparing. Do we want to compare CA, which is result minus whatever result points to minus whatever A points to, or do we want to do it the other way around? The condition is if whatever result is pointing to, in other words, whatever C is greater than A, then we want to perform the then statement. Otherwise, we want to go around. So there are two ways to do it. You can preserve the order of the comparison, but then you will have to do a J. We usually look for the opposite to get out of the conditional statement or to go to the else part. So that's something that we can do as well. So if you want to look for the reverse, we are looking for C is less than or equal to A. Okay, so that to me is the easier implementation. So that's why we're going to look for compare CA, and then we'll say J. So this particular branch, okay, the JZI is easy. Okay, if they are the same, get to end if. That's the easy one. But less than needs a little bit of thinking because it depends on the type. So now we have to look at what A is pointing to and what result is pointing to. Those are signed. So we are dealing with signed comparison here. And the question is, if we're dealing with a signed comparison, which flag should we pay attention to? There are, okay, so besides the Z flag, there are 4 flags remaining. One is C, one is S, one is O, and one is L. Okay, so you have to know, which one indicates ordering when you're comparing signed values. And it is, no, L, not S. Okay, we know S and O are very unusual that we will use them because sign by itself can not tell us the ordering when the subtraction has overflow. So overflow by itself is also not exactly useful for comparing, because if you're overflowing, then hey, that itself doesn't tell me the result of the comparison. The L flag is useful because it is combining the sign flag and the overflow flag. So when we're just comparing and just want to know which one is smaller in a signed comparison, we just pay attention to the L flag. The C flag is only useful for unsigned comparison. Okay. So in this case, JLI is the one to use. So we use another one, JLI, to also to end if. Okay. All right. So now, and end if is defined somewhere else. Okay. So if you want to do it this way, you can certainly do it. Like just define else if down here, and then you backfill and just insert. Okay, another chunk of code in between. Okay. So this way you don't have to leave space. Knowing that there's something there. All right, so now we have a choice. We can implement whatever is in the conditional statement, or we can continue after the loop, after the conditional statement. I would just finish the conditional statement first, which is result gets A. Okay, so with result get A, not saving anything into the previous registers, which I could have done, okay, because we got 3 registers to play with, we could have saved some of those things, or at least make assumptions in register C and register A. So assuming that we are not even doing that, we'll just recalculate everything, okay? So we'll recalculate what is in A. A is a parameter. So now we have LDI AA add AD, and then we have LD A. So at this point, register A is in fact parameter A. Okay, not what A points to, okay, which is not what we want in this case. We want the pointer, which is fine at this point. So now we can calculate the left-hand side, or the address of the left-hand side. We want to store this into result, okay. You can store it directly into what register D is pointing to, because register D is still pointing to result, so that's one way to do it. But if you want to do it the kind of sure way, you can load result as a label into register C, add CD. But this time you don't want to do a load, because now we have the address of result, which is a local variable in register C, and we want to change that. We want to change result. So we don't want to do a load, which is just reading. We want to do a store. So now we're going to store to whatever register C is pointing to, and A is the value of the right-hand side. So that's all we need to do here. So I'll just be very careful and make sure that this block of code goes into, where the insertion point is. And now we can finish up the program, because we just need to increment A, decrement N. Okay, so we do the usual stuff, LDI A, add AD, LD, put it into a different register, B in this case, and then we'll increment B, because B is the actual value of local variable A in this case. And then we'll store it back into A, and then we'll do, so that's why we'll do ST, whatever A points to, B. So are we doing okay so far with this sequence of code? Okay. You have seen this before already. We got a block of code almost exactly like this. I might have chosen to use different registers, but same idea, okay? We just want to increment A, and then decrement N is kind of the same thing. We have done that block of code already. So this is really just a repetition of that stuff. So we want to decrement N, so it's kind of the same thing. LDIA, this time with N, add AD, LDB, choose a different one, because we want to keep track of the address. We don't want to have to recalculate the address unnecessarily. And this time it's a decrement B, and then store that back to whatever A points to, and we're done with that. Is that okay? So now we're done with the 2 statements, like plus plus a and minus minus n. So when the loop is concluded, then we return the result. So that means, as far as the body of the loop is concerned, this is the body of the loop. So this doesn't end here. It goes all the way down here. Is that okay? Does everybody see how I use kind of like a brace, to indicate what range of code goes into the body of the loop? Okay. So outside of the body of the loop, we got fairly simple stuff to do. We just need to implement the return statement, and then we have the three opcode, exit code, and that's it. Okay, so we'll specify the return statement here. The return statement just wants result in it. So kind of the usual stuff. LDIA with result. Add. Oops. Okay, backspace. Nope. Does it have undo? Yep, it does have undo. Okay. Yep, that does work. So we have add AD, and then so this becomes the address of result, LDAA. That becomes result itself, and that's it. It's already in register A. Register A is the register that we use to return a value. So now we just have to clean up the stack. So don't forget to clean up the stack. All local variables should be cleaned up by the subroutine itself. We only got one, so increment D once is fine. So now the stack pointer should point back to the return address. So we just have to pop the return address into a register and then do a JMP. So that involves LD. Pick some register other than A and D. Okay, B is fine, C is fine. So now B has the return address. Increment D to deallocate the return address from the stack, and then the JMPB will bring us back to the caller where the call was done, well, right after the call. So are we okay so far with this code? It's a little bit long, but that's only because I kept talking, right? Yep.
Just kind of like a bit more information about the compare part. Like, what if we were to just like use A, comma C instead of C, comma A?
Okay. So, all right. So the question is, okay, if we look at this block of code, do we have alternatives? And the answer is yes, we have alternatives. So we'll say or. Now, in your answer, do not give me alternatives, okay? Pick one and just give me that one, okay? Because I'm not looking for alternatives. If you give me alternatives, I will read it and go like, okay. But if you give me one alternative that is right and one alternative that is wrong, it's going to be marked down. Because I don't want people just give me like a bazillion alternatives and go like, one of these has to be right. That's the infinite number of monkey theory, right? If you have an infinite number of monkeys, you're just banging on the keyboard. Eventually, I think it's Shakespeare, right? So I don't want to have to deal with that, okay? This is deterministic grading. I will only pick one solution to grade, and whatever that one is whatever score you're going to get. Okay, but it is not, since this part is instructional, we'll just take a look at what if we compare in the opposite way. Okay, so we'll have compare AC this time. So if you have a compare AC, then you're saying if A is greater than C, then we go into the branch. If A is greater than C, no, if C is greater than A, we go into the branch. Wait, let's see. What is C? C is whatever result is pointing to. A is whatever A is pointing to. So when C is greater than A, then we go into the branch. Right? Okay. So that means it's kind of easy too, because you can say now J Li, if A or whatever A points to is less than whatever C points to, then this time, but we need a new label. Okay, so we need a new label. I'll just call it then. Okay. But now you have to say, but if it is not, okay, then we need to branch around the entire thing to end if. And then the then label is right after the unconditional branch. So this block of code here does the same thing as the other block of code. So this block of code, 4 lines, is going to do the same thing as this block of code, which is 3 lines. And then the then label has to be, the then label is there. Okay, that's correct. Okay, so the then label can be exactly at that place. Is that okay? Does it kind of explain the alternative? Okay.
How long do we have? 1.5 hours?
You have 2 hours. You just have to pump yourself, with enough caffeine to last 2 hours.
One question will take around 30 minutes.
I mean, I'm talking, explaining, and writing at the same time.
But
So,
we will
hmm?
figure out.
I mean, there are a lot of stuff that is just repetitions, right? LDI, some register with a label, add the stack pointer to that register, and then that becomes the address of the thing, and then you do a LD if you want to get the value of that thing, you do a ST if you want to overwrite that thing. I mean, it's most of it is not really thinking, most of it is really just the time to write. So it makes a difference whether you're really clear in your mind of the concepts, because if you're really clear in your mind, what the concepts involved are, then it really is just, okay, I'm expanding a template, blah, 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 copy. You're just reapplying the template. You're stamping out cookies, right? Using a template. On the other hand, for someone who may not be understanding the concepts, clearly, then that person is kind of thinking and backtracking, and self-doubting, and then backtracking again. Then it's going to take longer. So the key to answer these questions quicker is to really fully understand the concept, okay? And not just say, okay, which template should I apply? Let's look back at tax code. You have to fully understand the concepts. Then you already know, oh, to get this done, this is what I need. To get this done, this is what I need, and so on. Is that okay? All right. All right, so we are moving on to the next question. This one is done. So if you guys want to, I can save this as a PDF and then upload it. That's perfectly okay. And you can even bring it to the test, which is basically telling you, nah, this is not going to be your question. But you can look at the format. All right, so question number 2 is to disassemble the following into C code. Be sure to indicate the types of return value, if there's any, the type of the parameters, if there's any, the types of local variables, if there's any. Also be sure to use structure code. There should be no goto in the C code. So I want you guys to give me while, if, using, if there's an else, use else, and so on. So I want you to give me structure code and not the flattened C code. Okay? All right. So we'll take a look at this and we'll say, okay, how do we get started with this? Now this was done in a slightly different style. This is done before I have labels. So that's why you can see that there are no references to labels. So now you have to track things on the stack on the piece of paper. You can put it on the same piece of paper. That's fine. In fact, that would be better because I can at least see that, oh, okay, you got the right idea. So if I assign points to the understanding of how things look on the stack, at least you get partial credit for that, okay? Because you have a picture of how things look on the stack. All right, so we'll take a look at this code and go like, well, where do we start? Well, we'll go pick up things that are easy first, okay? So what do you mean by easy things? We look at conditional branches and unconditional branches. And what we see is we have a label called L0, and L0 is defined after the branch to that label. Would that be okay, how many things typically have labels? If I don't give you, okay, so ternary operators have labels, conditional statements have labels, and then loops also have labels. So this tells us that, well, we have one of those 3 things, okay, at least. But what thing can I rule out almost immediately and go like, nah, it cannot be that? The label is forward. It's not a loop, okay? Cannot be a loop because in order to have a loop, the label definition has to be before the branch. Now, it can be a conditional branch, can be an unconditional branch. If it's a conditional branch, it means it is a do-while loop, or it suggests very strongly it's a do-while loop. And if it is an unconditional branch, back to your earlier label, there's a very strong indication it is a while loop, okay? Is it absolute? Not entirely, but that gives you a pretty good clue. So we know this is a conditional statement. And now we say, okay, what are we using to determine to get to that label or not? And what does that label actually mean? And there seems to be another label L1, okay? So we'll kind of scroll the screen and find out what label L1 is. So what we're doing, or what I am doing, is I'm trying to identify the structure of certain control structures in C and C++. Okay, well, that tells me that L0 is going to be a then branch. And an L1 is an else branch, and an L2 is the end of a conditional statement. How? Well, because L0 being the beginning of a then branch, and the block of code ends up with an unconditional branch over the other block of code to L2, that is a very, very strong indication that L0 is the beginning of the then branch, ending with the unconditional branch of L2. That makes L1 the beginning of the else branch, and L2 the end of the conditional statement. So I know I have an if, then, else statement within the subroutine. Okay? And it is not contained within anything else either, because we don't see any other types of labels, that indicates that this is nested within another control structure. Okay? And then we scroll down a little bit more, and then we see, oh, okay, I can see that we are ending the subroutine right at line 28. So line 28, 29, 30, by now you should really recognize those 3 lines of code like, oh, return. We were going back to the caller. Okay, so that means we only have one conditional statement in the entire thing. There might be some initialization before that, okay, but we can focus on looking at the conditional statement. So that's the control structure perspective. Now the next perspective is, well, what kind of stuff do we have on the stack? Okay, we know if there are parameters, they'll be on the stack. The return address is definitely on the stack, and if there are local variables, they're also on the stack. How do I know whether there are local variables or not? Line 3. Okay, line 3 clearly indicates that we have a local variable because I decrement the stack pointer. But you can say, but you also need to decrement the stack pointer if you're calling another subroutine and you're pushing arguments on the stack. Yes, but did I use that location right away? No. So that means I'm just reserving that space on the stack, which basically is kind of like a huge flag, saying, yep, we got local variables, and 1 byte of those. Okay, we got a 1 byte local variable. Okay, so now when you look at this code here, but I copy register D to register C before I decrement register D, and then I increment register C. So that makes register C pointing to one location above the return address. Okay? And what am I doing to that? Well, I'm copying whatever that thing points to register A. So register A actually has the parameter itself. Okay? And then I dereference the parameter to register A. So now register A is whatever the parameter is pointing to. So that tells me that we have at least one parameter, and it is of a pointer type of some kind. It's pointing to something. Okay? All right. So now I got enough to actually write down. Okay? So we have sub1. I don't know what it returns yet, so I'm not going to specify the return type yet. But we know it has one particular pointer, at least one pointer, and it is a pointer type. So we'll say param1 is a pointer. Is that okay? And then this is the beginning of the subroutine. We know we have a local variable of some kind. Okay, so we'll say there's a local var 1, but since I don't know what type it is, I'm not going to say anything here. And then we know that we are dereferencing param 1 some, at the beginning, from line 5, from line 4 to line 6, we're dereferencing param 1. Don't know what I'm using it for, but I know I'm dereferencing it. So I'm going to write it down here. So I'm doing something with the thing or the value that pointer 1 is pointing to. So now I'll continue to read the code, and continuing on line 7, okay? Line 7 says, oh, let's increment C one more time. Wait, C is pointing to the first parameter at this point. Incrementing C again suggests that we have a second parameter of some kind. Is that okay? So we say, okay, there's another parameter. What am I doing with the other parameter? Register C on line 7 is, after line 7, is pointing to the second parameter. Line 8 is dereferencing that, which means register B is the second parameter. And then line 9 is dereferencing the parameter itself. Oh, that tells me the param 2 is also a pointer of some kind. Okay. So now I go back to my partial C code and go like, okay, there's another parameter. We know for sure there's a second parameter, we call it param 2, and it is also a pointer of something. Okay, and we can also, say that we have param 1, we have param 2, and they're both dereferenced by the time we get to line 9. And then we compare. Oh, cool. That compare is used by the conditional statement because the result of the compare on line 10 is directly related to the conditional branches that relate to the conditional statement. So the comparison itself is a part of the condition of the conditional statement. Okay, so which way am I comparing and how am I doing the conditional branch and how is the local variable used? Okay, so we'll take a look at these things. So we're comparing A to B, so we're comparing param 1, whatever param 1 points to whatever param 2 is pointing to. And this tells us that JLI to L0. Remember, L0 is the then branch, okay? So that means we can now say this. Okay, this is my condition. It is in the conditional statement. So we now know, there's a if statement. And the condition of the if statement is like that. But not only that, I can now backfill. This is an integer. This is also an integer, signed. How can I know that right now? By looking at lines 10, 11, and 12, I can say, yeah, we know what parameter is pointing to. It's a signed integer.
Because JLI only uses a signed.
Exactly. Yep, good point. It's because JLI is only used to evaluate whether something is less than something else when they're interpreted signed. Okay, so that tells me that param 1 and param 2 are both pointing to signed integers. Okay. Now, if you look at this and forget to close a parenthesis here, I'm not going to take any points off. Okay, this is not about the correct syntax. It is more about can you recognize the structure of the code and pick out the elements. Okay. All right. So we now get into the then branch and try to figure out what the then branch is doing here. So the then branch is from L0 to the JMPI on line 23. So we take a look at this code and it looks kind of awkward, because remember, this is before the days that I had labels, and this is why labels are cool, because if I had used labels, you can identify right away and go like, oh, you're doing this and then you're doing that, blah blah blah. Okay. But without labels, you actually have to track what register C is pointing to, what register D is pointing to. Register D is pointing to the local variable, okay? And I'm copying A into it. What is A? What was A again? A was what param 1 is pointing to. Okay. So that tells me that we are doing something like this in C. Local var 1 gets whatever param 1 is pointing to. Okay, that's just line 14 itself. Line 14 is telling me that. And then line 15 says, let's decrement D. Let's decrement C, excuse me. Register C was pointing to param 2, now it points to param 1. So when I load A with C on line 16, A is param 1. Okay? Not what param 1 points to, but the parameter itself. And then I store B to A, whatever A points to, and B was coming from here. That was what param 2 was pointing to. So I'm storing whatever param 2 is pointing to whatever param 1 is pointing to. I think some of you recognize the sequence of code already, but we'll continue with this. Okay. So we got param 1 gets whatever param 2 is pointing to. Yep, it's the exchange sequence. So after that, from line 18 on, okay, so I increment C again, so C is now pointing to param 2 again, and then on line 19, B becomes param 2, and then on line 21, on line 20, I retrieve the local variable, because the local variable is still pointed to by the stack pointer. So on line 20, A becomes the local variable, and then on line 21, I'm storing the local variable to what pointer 2 is pointing to, okay? Okay, so typical exchange sequence here. Like so. And then I have this really weird line 22, which is just, oh, let's store a 1 into register A. And then it goes all the way to L2, which is the deallocation of the local variable and return. What was that? Yep, I'm specifying the return value, okay? So it is the same thing as having a return 1 in here. What about the else? Well, that's the only thing after between label L1 and label L2. And it's just putting a 0 into register A. Register A is what we use to specify a return value. So that becomes the entire subroutine. If whatever param 1 is pointing to is less than whatever param 2 is pointing to, exchange those two, exchange the values pointed to by the two parameters, and return 1 if there's an exchange, and return a 0 if there's not an exchange. Oh, that means the sub1 now has a return type. I really cannot tell whether it's signed or unsigned because there are no comparisons. So we'll just call it int. If you say unsigned, I'll count it as correct as well. Yep.
Wouldn't it be signed because you're, well, copying things? I guess it doesn't matter yet. I'm thinking of local var.
Oh, local var, yes. Yeah, local var is unsigned. It's signed, sorry. Yep. It has the same type as whatever param 1 or param 2 is pointing to. Yep.
Wouldn't the subroutine be Boolean and it's returning true or false?
But C has no such type as bool, B-O-O-L. So if this were C++, yes, you could call. If you say bool, I would count it as a correct answer too. Yep. But in C, there are no Boolean types. Yep.
Also, because all the params when they're used, they're all dereferenced.
Mm-hmm.
Could we just use it as call it just an int param 1 instead of a pointer to an int param 1?
Say that one more time.
So instead of having it as a pointer, couldn't you just make it an int and then leave off all the dereferences?
No. Because they mean different things. If you leave out the dereferencing, including the types of the parameters and then how you use those, then you would exchange the parameters instead of what the parameters are pointing to. In C++, you can sort of do that by using ampersand in front of param 1 and param 2, so they're now passed by reference. But if you use pass by reference in C++, then you have to remove all of the asterisks in the code because they are not pointers anymore. They are now parameters that are passed by reference. But since I'm only using C in this class, this is what I use. Yep.
So for the comparison, how would we know that we're not comparing the addresses of the pointers and instead comparing the content from the code that we have?
Because of line 6 and line 9?
Exactly, yeah. So how would we, if we go to look at the line 10,
Uh-huh.
Because if you're loading the content, like suppose into registers A and B, and then doing the compare, wouldn't it be just like the parameters themselves?
If I did not have line 6 and line 9, then I would just be comparing the pointers and not what they're pointing to. But because of line 6 and line 9, register A is not param 1, it is what param 1 points to. And then line 9 makes it compared to what param 2 is pointing to instead of param 2 itself. Okay? So you can kind of expect something along this line in your test where I may not be using labels at all and now you start to appreciate the use of labels, because once you use labels, then you don't have to in your head keep track of where's register C at this point. But that is important because I need to know whether you know how things are on the stack and how to get to different locations. So you will definitely see something like this in your test. So you will have to track register C and all the other registers to find out okay, what is the current value in that register. Okay. All right. So if this one is good, we move on. Question number 3. Which instructions mentioned in mnemonics rely on the combination of PC mux equals to 0 and PC inc equals to 1? So this one is testing you on the architecture thing.
Do we have these questions also?
Do you want to have these questions also? No? Okay, well, we exclude the architecture questions then. I have to remember that though. Yeah. Okay, that's fine. Okay, so question 4 is definitely based on stuff after the second exam, or when the second exam would have happened. And this one is about comparing 16-bit numbers instead of 8-bit numbers. Okay, so little endian means the least significant byte of a multi-byte integer is stored at a lower address. Assuming that we use little endian convention to pass 16-bit integers by value, the following C code, implement the following C code in assembly. So this is all I want you to implement. Okay, I'm giving you 2 parameters. Parameter X is a 16-bit number. Parameter Y is also a 16-bit number. And I just want to know whether they equal to each other or not as 16-bit numbers. Okay. So the hint is important. The hint is try to think of the comparison of -1 to 1 and 1 to -1 and how the values are represented in 16-bit binary form. And the following helps you understand what it is. So this is what the stack is going to look like when I pass 1 as X and then -1 as Y. These 2 bytes, okay, and I think I also specify left-hand side is lower address, so the return address is at the lowest part of the address. The next byte up is 0, 1, the next byte up is 0, 0, then the next byte up is FF, then the last byte is also FF. So you have 5 bytes on the stack when I pass 1 and -1 as parameters. So this illustrates what is little endian, because how do you represent 1 as a binary number, as a 16-bit binary number? If you spell it out, okay, as a 16-bit binary number, it would be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, right? But if you look at it as 2 hexadecimal numbers, 2 digits to each one, it would be 0, 0, 0, 1, right? But 0, 0, 0, 1 needs 2 bytes to represent because there are 16 bits. So storing the 0, 1 first is what little endian means. The least significant byte is at a lower address. That's what it means. Okay? So now the question is, given that information, how do you compare 2 signed numbers when they're passed on the stack? And each signed number is a 16-bit number. So how would you do that? Yep.
So in order to tell if it's a negative or positive, we probably have to look at whatever is on the rightmost, like whatever.
The most significant byte is important if you want to determine order, but this subroutine is a lot easier. It just wants to know whether they are the same. So if you want to know whether they're the same, it doesn't really matter. Do you compare the least significant byte first, or do you compare the most significant byte first? Doesn't matter, right? If at least one of those two bytes is different, the two numbers are different. You don't even need to compare. I mean, you don't need to determine which one is smaller. Question?
So would you compare the one first? If
Yeah.
they're the same, compare the second one?
Yep.
And then if they're not the same, that's
Yep. Yep. That's how we do it. Okay. So the code to do this is going to be like the following. Okay. I need enough of the C code to be visible. Okay. So EQ16. Do you want me to use the symbolic names or not symbolic names? I think symbolic names makes it a little bit easier. Okay. Okay. So if you look at the symbolic names, okay. Okay. So if you look at the symbolic names, my palm was touching the other window. I might need to move that so my palm cannot touch it. Okay, so when you look at the symbolic names, it has no local variables. So return address is going to be 0. The next byte up is going to be X, but we want to differentiate this time. This is the least significant 8 bits of X. So this is going to be return address 1 plus. The next one is going to be the high byte or the most significant byte of X. So this is going to be X underscore low 1 plus. The next one is going to be Y low, which is X underscore high 1 plus. And then the next one is going to be Y underscore high, which is Y underscore low 1 plus. Is that okay? That tells us, how the stack looks like, which corresponds to the hint. Return address is there, and then X low is this byte, X high is this byte, Y low is this byte, and then Y high is that byte. Is that okay? So all we are really doing is comparing X low to Y low, and then we are comparing, if that turns out to be the same, then we'll be comparing X high to Y high. Okay? If X low does not equal to Y low, we can exit right away and just return 0. Okay? So the rest of the program, or the rest of this subroutine, is really kind of what we usually do. Okay, so we have LDI, register A with X low, and then add D to A, LDI B with X Y low, add BD, and then we compare those two. Okay, but we have to dereference first, so we have to do LD AA, LD BB, CMP AB, and then JZI to more test. Because if they're the same, then we have to look at the high byte. Okay, but if they're not the same, then we can LDI A with 0, JMPI to a label called return, and then continuation up here. I mean, you do have more space on paper, but I don't want to keep scrolling around, so that's why I use this notation. All right. So what if I need more test? Then we define the label more test over here. It's going to be the same thing, except we now deal with a high byte. So LDI A X high, add AD, LDI A B, Y high, add AD, LDAA, LDBB, CMPAB, and then we have another JCI. So JCI, so this time if it is equal to, then we know for sure that we can return 1. Okay, so we'll say, in this case, return 1. Otherwise, we load 0 into A, and then jump to return. Now we can define all those future reference or forward reference labels. Okay, so return 1 is here. All it does is to put 1 into register A, and then return as a label is just the 3 instructions that we use for returning. So I cannot use register A because register A definitely is meaningful here. So we have to use register B. It is now the return address, the allocated return address, and then continue in the caller. So that becomes the entire code for this particular question. So having the labels, I think is really helpful, because it's easier, much easier to get to the value of a particular thing on stack. Is that okay? So this one, the difficult part of this part is to understand what is little endian from the example and the explanation. All right, last question. Moving on. Sure. Okay. Yep.
Isn't we have like LDI B and Y high. Is it going to be add BD or AD?
BD, that you're correct. Okay, good job. Good. Spotting the error here. This would be BA. Yep. Thank you. All right, so are we good? All right. Moving on to question number 5. Question number 5. Oh, this one I like.
Where did we use return 1?
Huh?
I think I missed it on the other question.
What? What did you miss?
One,
Say again?
return 1 label.
Return 1. I defined it.
You did define it, but where did we use it? Oh, yes, JCI.
Yep.
I missed it.
Yep, because if both the low and the high bytes equal, then they're the same, and in that case we have to return a 1 because we're looking for equality. Okay, question number 5 for 5. This is my favorite because this is a single statement, assuming sub 1, sub 2, sub 3, and sub 4 are all defined and they're all expecting one single integer as parameter. How do we implement this one single line, which is a function call? Okay. So you look at this and go like, okay, I don't know how to do this. Well, that's not helping. So you have to know how to read this code, okay? The first thing is forget about reading from left to right, because in the subroutine call, okay, the last parameter is pushed first. So when you're looking at parameters, read from right to left, not the other way around, okay? So you look at this and go like, okay, eventually I want to call sub 1, okay? So matching parentheses is kind of important. You can see how this is one pair, which is the else of a ternary operator. This is the then of the ternary operator. The one is the else of the ternary operator. And then the condition of the ternary operator is this part here. But that is the second argument that you need to pass to sub 1. The last argument you need to pass to sub 1 is pretty easy. What? Okay, so. Huh? No, the subroutines are done. Okay, you can assume the subroutines are already implemented. You are just calling those subroutines because otherwise you need to know what the subroutines are supposed to do. Okay, and the question doesn't tell you what the subroutines are supposed to do. All right, so since I can use this, I can just mark it here. This is the last argument to sub 1. This is the second argument of sub 1. This is the first argument of sub 1. Is that okay? So the second argument to sub 1 is kind of complex, but it is parsable, right? is a ternary operator. This is the first part of the ternary operator. This is the second part of the ternary operator. This is the third part of the ternary operator. Of the second part of the ternary operator, we just have to call sub4, whatever that returns, add 1 to it. And then as far as the first part of the ternary operator is concerned, we call sub1, we call sub2, and then we call sub3, and then we compare the return values of those two. Is that okay? So the very first thing we need to do is what? In order to implement this line of code, what is the first thing we need to do? Decrement the stack pointer and then push 3. Yep, we know how to do that. That's the easiest, well, that along with pushing 1, those are the easiest part of the question. So we have LDIA3, decrement D, STD3. That will take care of this, right? Now, in your code, you don't have to specify all of these pointer things, because I'm looking at the solution. But if you do that pointing thing, that will actually help me understand your code, so that's helpful too. Okay, now we are ready to push the second argument that in the call to sub1. I can't do anything until I know the result of the comparison. So the first thing we need to do is to find out what is sub2 returning. Call it first, right? Call that, figure out what it returns, and then call sub3, find out what it returns, do the comparison. Then we know which way to go. All right? So I'm looking. Well, we have the LDIA dot 6 plus, okay? And then we decrement D, STDA, and then JMPI to sub2, okay? So this is corresponding to that, okay? But since the return value is stored in register A and, that's going to be overwritten by the call to sub3, let's push it on the stack. So we'll do a decrement D, STDA, oops, the other way around. Then we can call sub3 now. Okay, LDIA dot 6 plus decrement D, STDA. Oh, right. Okay, forgot about the push on the 20. Decrement D, STDA, LDIA dot 6 plus decrement D, STDA, JMPI to sub3, increment D, right? Because the argument on the stack, that needs to be deallocated. And then we can now retrieve the saved return value of the call to sub2 into another register. So we'll do LD, we'll put it into register B, increment D, and now we can compare. So we have a CMP. B is the return value of sub2, and then A is the return value of sub3. So once again, you can choose one or the other way. You can look for a way to branch to the else branch, or you can choose a way to go to the then branch. So the typical way is to look for a reason to go to the else branch. So we want sub3 to be less than or equal to sub2, or the return value thereof. So we have compare AB, J, and let's see. The return types are all 8-bit signed integers, so we have to use JLI. So JLI to else, JZI to also else. So now we are at the then branch. Okay. Okay, so we're now at the then branch. The then branch is 1 plus sub4 11. So that's LDIA 11, decrement D, stda, and then we call sub4 LDI a dot 6 plus decrement d stda jmpi to sub4 increment d to deallocate the parameter, and then remember to add 1 to it. So so that's going to be increment a, okay, jmpi to end if, because otherwise it's going to fall through to the else case. The else case is 1, easy peasy. LDIA with 1. So at the end if here, we just have to push whatever a is on the stack. So we have a decrement d LD, st da. So that takes care of the second argument. Now onto the first argument. First argument is just 2, so we have a LDI a2 decrement d stda. So now we have all 3 arguments on the stack. It's time to call sub 1. So we have LDI a dot 6 plus decrement d store to d whatever a has jmpi to sub 1 increment d increment d increment d. That's it. Okay, did it in 10 minutes because that's all the time that I had. But do you see how you kind of unravel the whole thing? You look at the C code, and then in your head you have to think about the ordering. What do I need to do first? What can I do first? And then what can I do next, and so on. So in this particular case, there are several things that come in that are important. One has to do with last parameter is pushed first. So you need to first identify what is what parameter, okay? 3 is the last parameter of sub 1, and that's the final thing, the last thing I want to do. Second thing is you have to understand what is a ternary operator. Basically, it is an expression that is a conditional statement by itself, okay? So with a ternary operator, you definitely have to evaluate the first one first, which is the condition. If the condition is true, then you evaluate the second part of the ternary operator, and if that is false, then you evaluate the last one. Okay, but that entire expression from here all the way to here is really just specifying a single value that is serving as parameter 2 of sub 1, sorry. And then we have a constant of 2, also as the first argument of sub 1, so that's an easy one. Call the whole thing. The second thing that's kind of important that I will be looking for is you have to remember to deallocate arguments when it's done. Another tricky thing here is whenever you're comparing or you're using the return values of 2 consecutive subroutine calls, remember that the return value of the first subroutine call is going to be lost by the time you have the second subroutine done. So you have to push it on the stack, retrieve that, then do something with it. So those are the concepts that you need in order to get this one done. Is that okay? I understand if I can do it in 10 minutes doesn't mean that you can do it in 10 minutes, but I can expect you to be able to do it in half an hour. Okay? Yep. Yep. So once again, I'm going to save this file. I'll head out to the lab. There are no new activities to do in the lab, but it would be a good time for you guys to kind of review the material. If something that you have been trying to get working, like Fibonacci, and it's not working, you can show me, what you have, and I can help you debug that code. Okay. If nobody is asking me questions, then I'll push this, onto Canvas. And this is going to be the one that is specific to this class. So on the Tuesday, Thursday class, it'll be the same practice exam, but I'm going to rework all the answers. So it's not going to be like, oh, just watch the video of the Monday, Wednesday class. That would be the easiest way and the laziest way to teach the Tuesday, Thursday class. Yep.
Do you have exam 2 with you? Or?
No, I don't have it with me, but I do have it scanned. So you have questions about it, I can bring it up. All right. Okay, so let's get out of the classroom in case there's a next class coming in. Nobody seemed to be at the door, so I don't think we have another class coming in.